All right, so let's now learn about how we can do a precise calculation when we're working with a standard normal distribution. And the reason we're studying this method to do a precise calculation is that apparently when you're on a normal distribution generally, or now specifically we're working with standard normal distribution, the empirical rules that we have learned has a limitation. It can only handle, the set of empirical rules can only handle finding areas where your z-scores are limited to whole value z-scores only. But now we need to overcome that limitation by working with, we're still going to find area on the bell curve, but what if the z-score is in decimals, say a 1.75, and we want to find some area between 1.75 and 0.25, for example. Okay, so how can so empirical rules is not able to handle a situation like this where z-score is being in decimals. And so now we're going to learn that method to come up with a precise calculation and to overcome the limitation with empirical rules. And so now once again, we're on a standard normal distribution, and my aim of this video is to entirely focus on the method that start out based on the standard normal distribution, this precise calculation method I'm about to show here. So assuming we're on a standard normal distribution, the n 0, 1. And so the method I'm introducing here is a method that in my own term I call it's a left area method. But it's a quite original method. Before any technology was designed to handle, then this method came out long ago. It started out being introduced as the Z table, and then as technologies become more advanced and more advanced, it keeps getting better and better. But in the end, the original method here is what I see as the left area method. So the idea of the left area method is that, generally speaking, doesn't matter where you're at on a bell curve, doesn't matter which value you're looking at on a bell curve, and here specifically we're looking at the z bell curve right here. Then at any z-score, there will be a left area cumulatively shaded to the left hand side. And so let's call this value some z-score a right here. And this shading area, symbolically, it's written as the probability where z-score is being less than or equals to a. And that's why I call it's a left area method. This is introducing a left area. And so this left area right here, there are plenty of software over the web right here that can help you find the left area cumulatively shaded to the left hand side of z-score. Just fundamentally, the only one fundamental to keep is that any z-score, doesn't matter where your z-score stands. You have a z-score here, you have a z-score here, you have a z-score here. Any z-score will have an area shaded to the left. And in these modern day right here, there are plenty of software, including online tools that allows you to find areas to the left of any z-score given. And so to get really practical, let me introduce one little example over here. And everybody is going to understand what the left area method is all about. Once again, let's say we're on the standard normal distribution. Mean here is 0, sigma 1, or population standard deviation equals 1. And any values here is a value of the random variable z. And then here, let's say I'm looking at a z-score being 1.25. Okay, so this z-score right here, first thing to notice, it's no longer a whole value z-score. And so this is where, as I said earlier, the empirical rules fail to work right here. But in the end, right after what I have just now explained, then doesn't matter where your z-score stands. It will have a cumulated area totally or cumulatively to the left-hand side. And here let's find, in this little example over here, let's find how much, and that shaded area is the probability that on this standard normal distribution bell curve, we have a z-score being anywhere less than or equals 1.25. And so, just as I was saying earlier, there are plenty of software programs as well as online tools that allows you to quickly and precisely calculate how much area cumulatively to the left-hand side of this 1.25 right here. For students who are actually learning statistics with me right here, over years I developed for them a little program, a little portable program on Microsoft Excel right here. And so let's have a look at my Microsoft Excel screen right here. But so it's just in the effort for to save my students time to surf the web and all that. But you don't have to use this tool if you don't like it. But so once you open the file, then down here this same file that's called programs.xlsx right here. But I designed about 6 little different programs being written in 6 different Microsoft Excel tabs right here. So the one we're about to use right now is called the LSND program. And it can be found right under that tab of the very first tab of your program's file. And so all it is simply, you can just simply hit, or you can just simply type the z-score 1.25, or on this bell curve is 1.25 is there, you type that z-score into the designated box right here being highlighted. So 1.25, and you hit enter. And notice, so now the highlighted box is being moved to a different one. So later on, if you want to change to a different z-score to do your calculation, then we can just simply use a mouse and click on that box again. And so this box, and by the way, never change that box. We only want to stay in this box right here and enter a new z-score anytime you want to do a new calculation. But here, so 1.25 for my z-scores, once being entered, the next box here will automatically calculate and give us here a very long, lengthy decimal value. But this is how much the area. So back on my picture, so 0.8943502 is, and of course it should be a lot longer than that, but Microsoft Excel usually only show about 8 decimals, but Microsoft Excel actually knows a lot further decimal expansion. It's just it's only showing on screen here about 8 decimals. And if you are actually an expert with Microsoft Excel, you can also go back and adjust. And once you download the file and have in hand right here, you can also adjust Microsoft Excel to display more decimal places as you want. But so what is this decimal is indicating? This decimal is how big that area be cumulatively shaded to the left-hand side of my z-score 1.25. Or thinking as a percentage, then this area cumulatively shaded to the left, and I talked a little bit when we began talking about normal distribution that this area shaded to the left side, starting from 1.25, shaded cumulatively to the left hand side will never end. It's actually going to keep extending further, but becoming a weeny tiny tail out there. But all that area cumulatively, no matter how it further extends to the left hand side, but all that area accumulates to about 89.44 if we round to 2 decimal places, but percent. And so that's about a different way how we're expressing that. But see, it looks just about consistent, and of course, anyone viewing this video must forgive me in terms of being slightly off scale, but that's not the point. The point is to understand the generality right here. And so, but like I said again, this is only one tool I designed first. Originally, it was intended for my students enroll in my class, and if you're interested in a copy of that, then you can feel free to message me, and I can forward over a copy to you. Or even if you or you might even have a Microsoft Excel background, and you can even program make that program on your own. But so what's the idea about LSND? Why do I name it that way right here? So SND, as I discussed in my video lesson earlier, then S is standard normal distribution. So this is standard normal distribution, and the L right here stands for left area. And so that's what the left area for is, something to remind yourself. So this program is only intended to give you the area to the left of any z-score. And it, see, the SND standard normal distribution. So this program is designed, I wrote it to specifically only handle when you're giving the value there being a z-score. And so let's find out a quick little other example right here. So what about when we are assuming again that we are on the standard normal distribution? The z variables on the horizontal axis, standard deviation equals 1. Let's say I'm going to pick another z-score out of my own creativity. How about negative 1.35? And so just like what I said earlier, any z-score from wherever it stands, either to the left-hand side or to the right-hand side of your bell curve center of your of 0, it's always going to have an area cumulatively shaded to the left-hand side. And that area there, symbolically, it's stated as the probability of having a z-score. That area, that accumulated area, represents the probability that on this bell curve we find a z-score less than or equals negative 1.35. And so now after we've had a little bit of experience with the earlier problem, you can either use your online tools or even the z-table traditionally, or use the LSND program I wrote here, if you have a copy of that. But so now in the LSND program, running the LSND program right here, then simply just go into that box right there where it's designated z-score, and please never change that box, never change this box, and never change that box. Only change to different values here in this designated box right there. But so now negative 1.35, hit enter, and so now my value of that area now is being so that area now cumulatively it's 0.088508. Okay, or so formally speaking, the answer here is 0.088508. Okay, and how far to round normally when you're doing your assignments, every assignments that, and here I'm specifically speaking to the viewers who are actually my students being in my introductory statistics course. For now, as a general lecture, I'm leaving just whatever the final answer is here, but a lot of time maybe you're going to be asked to round it down to 4 decimals, or even only 2 decimals or 5 decimals. It all depends on different problems. But then you can understand that another way to understand this decimal is that the accumulated area on to the left-hand side of my z-score, negative 1.35 on this standard normal distribution bell curve, is only about 8.85% compared to the whole bell curve. So what's the impact here? The entire bell curve is permanently 100% or 1. So out of that entire 100% or 1 right here, my area cumulatively to the left-hand side of this designated z-score is only taking about 8.85%. About And so now, before moving out to different types of example, then anyone could have asked me this question right here, that regarding any of the very previous example right here, that so on a standard normal distribution, throughout most of and pretty much all of our examples so far, I've been using this inequality that has the equal sign. Say in the first one, and even back in the examples I was working on the empirical rules, the situation happened, I was using all of those times, I was using the inequality that came with the equal sign right here. And yes, the bell curve drawn with the shaded area was looking like this. So 1.25 somewhere here, and we no longer have to worry about how far is 1 and how far is 125. But namely, this is a cumulatively shaded area to the left-hand side. Okay, or in a later example, we had another one, like say find a probability where z-score was less than or equals, and had that equality signs again, and negative 1.35, and we learned, and once again, on the bell curve right here, okay, z-score, okay, and center at 0, this time at negative 1.35 maybe out here to the left-hand side somewhere. And then I was making that shading to the left-hand side. Okay, and so anyone viewing those examples throughout my earlier part of the video could be asking or having in mind, what if there were no equality, meaning going back to any of these problems right here, but the inequality was only a strict inequality, or here's the same thing, just a strict inequality, just strictly less than 125, or z strictly less than negative 1.35, would it be the same way to find the answer, and will the answer be any different? So the answer to that is there are no difference in the answers. No. So having no equality in any of our problems here makes no difference. Okay, make no difference in the final answer, or basically in the answer, or in any of our final answers. And then as well as no difference, neither any difference in the way how we do it. So okay, and as well as no difference in the methods. Doing it. Okay. So meaning if you are using my LSND program, it's just be the same thing. You enter the z-score designated. It would be any other online tool that you're using, or even your calculator, or any other technological resource you have. And the way you do it it's just as the same as the way how you were doing it when it was having that equality sign.